Okay, hi once again everybody. Welcome back to our Calculus 3 class notes. We're on page 111. Looking at example 97, and we're talking about substitutions in triple integrals, which essentially is a transformation of the triple integral. Okay, so I'm going to show you how we got we're going to transform an integral that's in the rectangular coordinate system into an integral in the cylindrical coordinate system. But remember, we're thinking of this in a backwards way, right? So really, what we're thinking of is we have some sort of wedge like this that looks very like, okay, this is going to work with polar coordinates. So that's why we don't have this. We have this. We're thinking about, we're working towards this, even though we're really working from this to what we're at. Now, the way we do that is we make these coordinate transformations x equals, and we're using r and theta instead of u and v here because we're used to this being r and theta. So x equals r cosine theta, y equals r sine theta, and z equals z. That's the familiar transformation from the rectangular coordinate system to the polar coordinate system. Okay, and the cylindrical coordinate system because we added the z term, z equals z. And so what would the Jacobian be here? Right? Basically, again, working backwards, this region in the xy plane that works well with polar coordinates, after this transformation, we can think of it as coming from a rectangular region in the r theta z plane. Okay, so the way we do that is through the Jacobian. Now, the Jacobian of r theta and z, that's partial of x with respect to r, theta, and z in the first row, and then partial of y with respect to r, theta, and z in the second row, and partial of z with respect to r, theta, and z in the third row. Then I evaluate each one of these. So the partial of x with respect to r is cosine theta. Partial x with respect to theta is minus r sine theta. And the partial of x with respect to z is 0. There's no z in x equals r cosine theta. Partial of y with respect to r, sine theta. Partial of y with respect to theta, r cosine theta. And then there is no z in there, so the partial of y with respect to z is also 0. Then the partial of z with respect to r is 0, partial of z with respect to theta is 0, and the partial of z with respect to z is 1. So it turns into a pretty simple evaluation. Remember, so it's the first value here, cosine of theta, times the 2 by 2 that is not underneath that cosine theta. So that's just cosine of theta times r cosine theta times 1 minus 0. So that gives me r cosine squared theta. Then you have minus a minus, so plus r sine theta minus the minus r sine theta times the 2 by 2 that is not in the column or the row of that guy. So that's sine theta times 1 minus 0. So that's plus r sine theta times sine theta. So that's r sine squared theta. And then I have 0 times that 2 by 2, so it's gone. So then it's just understanding using trig identity, the Pythagorean identity, that cosine squared plus sine squared theta equals 1. The Jacobian just comes out to be r. So thus, the dx, dy, dz is rewritten as this Jacobian, the absolute value of the Jacobian, dr, d theta, dz, which is just r, dr, d theta, dz. And that r, I can just drop the absolute value signs because we're always assuming r is the positive radius, the positive distance from the origin to whatever the point is in the r theta plane. All right, likewise, if I can imagine having this in the rectangular coordinate system x, y, z, but it lends itself much better to spherical coordinates, then I can think of those spherical coordinates coming from this transformation where in the rho, phi, and theta plane, it's really a cube. Okay, so with these transformations, x, y, and z, again, I can plug it into the Jacobian and you can work through each of these pieces. Must have cut off the line on this side, but there is a line on that side. All right, so it just means the determinant. So I take all these after some simplifications, and I can let you work through all that. They're not hard simplifications, and I'm pretty detailed here. You end up with the familiar rho squared sine of phi that we just magically threw into the integral back in 15.7. So we actually know the mathematics now behind why that rho squared sine phi gets put in the area element or the volume element d rho d phi d theta.